Thanks for the introduction. So I'd also like to thank my other co-authors, Piertimo Bremer, Ray Grout, Hemant Kola, Jacqueline Chen, and Valerio Pascucci. And the three guys in the middle there are application scientists, so they deal with combustion primarily. So what I'm going to be talking about here is really taking something that people do in the combustion field in turbulent flow analysis and seeing, if we apply techniques from the visualization community straight to this, what can we achieve? So a bit of history. Oh, it's cutting off the slide. That's okay. Lipo Wang and Norbert Peters in 2006 introduced a new technique for the analysis of turbulent flows. Basically, they came up with this idea that if you partition the data into these regions that flow to the same minimum-maximum combination, then you get a unique decomposition of your domain that should relate very well to the underlying structural properties of your flow. And so this is the definition in their paper, which is the ensemble of grid cells from which the same pair of extremal points is reached via gradient trajectories determines a spatial region which is called a dissipation element. So for those of us in topology, this should sound very similar to what we've been doing the whole time. So then they went on to actually do some analysis with these dissipation elements, and they characterized them primarily by the distance between the extrema, so the maximum and minimum, and the function value between them. And this middle plot here basically shows, each dissipation element is thrown on there, and this is the density profile of the dissipation elements in a flow. And what they were able to find is that if you actually look at the conditional mean of the scalar difference conditioned on the length of a dissipation element, and you do some compensation, what you get is the fact that these things behave very much as is predicted by Kolmogorov's 1/3 power scaling law for the structure function. So this was very nice, and they came up with a nice coefficient for this scaling. So this work then started a whole new series of papers in the turbulent flow community. Basically, they started looking at relating vorticity and strain in terms of dissipation elements, relating scalar dissipation and vorticity, identifying turbulence regions and doing statistics based on that, comparing simulations with experimental measurements, looking at dissipation elements in particular in the experimental measurements and seeing if they matched what was predicted in the direct numerical simulations. And then looking at conditional statistics for wall-bounded flow. So there's a bunch of work that followed out of this. So it's a success story, great. Why are we revisiting it here? And here, these are images from the original publications, and having seen many of these images before, you immediately notice that, you have these strings of extrema, in 2 dimensions and 3 dimensions, and anybody who's done topology with this kind of data will say that, this is typically at the resolution of the grid. You have small numerical errors, or maybe it's a flat ridge line, and therefore exactly how the data is interpolated on that at that resolution is going to affect whether or not these extrema appear. So these are also each new critical point is going to add a whole bunch of dissipation elements to your statistics that you're trying to base your theories and laws about turbulence on. So then the question is, do these actually matter? And we can envision some pretty simple scenarios that would highlight why you would be concerned about this. For instance, I have a ridge next to a valley. On the left is the unperturbed version. Here I have one dissipation element from the bottom of the valley to the top, and it has a certain length and a certain scalar difference. If I modify this function by 1/10,000th of its function range, I tilt it a tiny bit, I get a completely different sized dissipation element if you're characterizing it as the Euclidean distance between the minimum and maximum. So change the function by 1/10,000th, now you get almost a factor of 2 difference in the length. if I add very low amplitude noise? So this is again 1/10,000th of the function range. I just added some noise in there. Because the ridge and valley are flat, it ends up creating a whole bunch of new critical points. And now I have a whole different view of the statistics I would generate looking at these dissipation elements. And the more challenging part here is that there's no real means of reasoning about the stability of the analysis you get out of a dissipation element-based approach. So, just to recap, since this is the third talk in a topology session, I probably don't have to go into Morse functions too much, but all right, here we go. So if f is the scalar valued function whose critical points are non-degenerate, that is the Hessian matrix is non-singular, then we call f a Morse function, and in the neighborhood of a critical point, the function has this nice representation, right? It has a nice continuous gradient field. You can trace lines in this where an integral line or gradient trajectory, I'm going to use them interchangeably, basically are tangent to the gradient at every point along the line, and they have natural lower and upper limit points at critical points of a function. So we'll call them sources and destinations. And gradient lines or gradient trajectories are distinct and perpendicular to contours. Okay, we can start grouping gradient trajectories. If they're grouped by the source, then we'll call them the ascending manifold. So for instance, on the left there, the orange region is the group of gradient trajectories that originate at that minimum in the middle. On the right here, in the green, you have the group of gradient trajectories who flow up to the maximum. There's one key difference here with how the flow is described in the dissipation elements, and that is the original paper by Wang and Peters did not acknowledge the fact that integral lines can actually end up as saddles as well, which we know to be a fact in Morse theory. So here we also have those arcs that actually end up at the saddle points. Okay, so you intersect them. For a Morse field function, this intersection is non-transversal. And these functions are dense in the space of functions, so it's not like we're creating some huge sin in viewing our input data as a Morse field function. We have the Morse field complex, where within any region, every single integral line is going to flow to the same extremum combination. And so, very simply, we can extend the definition of dissipation elements to topological dissipation elements, which is a topological dissipation element is formed by a minimum maximum combination, and it's the set of D cells of the Morse field complex formed by the intersection of the ascending and descending manifolds of the minimum and maximum respectively. So very straightforward definition. So what can we do with this? Why go through this exercise? And this is really the whole point of it, which is we have very well-established machinery and Morse theory for simplifying functions and looking at a multi-scale representation. So on the top left, I have a one-dimensional function that has some slight perturbations. I can identify neighboring critical points, and the index lemma tells us that we're allowed to do this. And we can simply remove them in a combinatorial way, and we obtain a coarser representation of the function. And now we can start reasoning with the coarser representation as well. And this works in 2 dimensions and 3 dimensions and so on. So of course, we have to compute a Morse field complex, and we finally reached the point in the field where we can do this on par with the geometric accuracy of integrating things, which is very nice. So we use the geometrically accurate discrete algorithm we presented at Viz in 2012 to compute a discrete gradient field. And so that takes a continuous gradient field, which is on the left, and maps it to basically pairing of cells, inside of which tracing ascending and descending manifolds simply becomes traversing through the pairs and the face relations of the cells of the mesh. So I can do a breadth first search from a maximum to compute its descending manifold. I can compute another restricted breadth first search from a minimum to compute the ascending manifold, and that gives me a region. I connect the dots, and there's my topological dissipation element. So very simple to compute. And now that we have a robust structure, a full Morse-Mel complex, there are also techniques to simplify this in the literature. Okay, so we have a numerical definition and a topological definition. How are they different? Well, on the very left, we computed a bunch of streamlines that labels voxels, the centers of voxels, as the dissipation element. In the discrete case, we take the intersection of the ascending and descending manifolds, and for full disclosure, we take the closure of the cells also. So we look at the boundary flows as well to get us connected all the way from the minimum to the maximum. And so we get basically a submesh of our input mesh, of a refined version of the input mesh that represents our topological dissipation element. In the numerical case, they didn't actually say how extrema are detected, other than it is where the streamlines end. So I assume that is some kind of extrema or numeric detection. Could be based on a simple threshold that says if I'm integrating a line and my local gradient is less than a certain threshold, I terminate. On the other hand, in the discrete case, the extrema are detected combinatorially. However, there's also certain conditions basically that force extrema to appear. For instance, and there are certain differences in the segmentation you get out of it as a result. So in the numeric case, I'm allowed to do things like have that isolated dot of that is part of a dissipation element, whereas in the discrete case, since we try to keep things coherent, we're restricted by the resolution of the mesh in representing certain features. And whether or not that actually matters is something that maybe we could debate. So let's look at a simple example in 2 dimensions. On the left, top left, you have the dissipation elements computed through integration. Basically, just start a streamline upwards and downwards from each grid location and color according to the origin and destination. In the topological case, we go through the discrete Morse theoretic approach with the accurate geometry algorithm. And on the right here, basically, are the 2 images overlaid, where I took the segmentation from the numeric image and overlaid the boundaries from the topological image just to get a slightly convincing picture that we're pretty much looking at the same things here. And while the geometry tends to agree in a lot of places, in some places it's not quite there. So if we actually compare these 2 techniques and try to pick a winner, well, the first point is that in the numeric version, there's no accounting for flat regions or degeneracies. So what happens if you accidentally hit a saddle, or you accidentally hit a almost flat region where your integration simply stops? The nice thing is in the topological setting, we have simulation of simplicity, which gets us through all of this, and we're able to construct a robust representation. However, the numerics do give you accurate integration. And yes, you accumulate error over the lifetime of a streamline, but you can bound that, use higher order techniques, and you get very nice looking results. Where in the discrete Morse theory based approach, you have discretized geometry. Things are going to be forced to merge together, maybe where you don't want them to. So you get a better geometric representation out of integration. Okay, both of them have artifacts. In particular, in the numerics, basically you can have short wavelength noise that happens maybe just because of your order of integration. You can have problems where a critical point is detected right on the boundary of 2 of your grid cells. So how do you label it, which one? And you can have crossing streamlines, so it's not guaranteed to be consistent. In the combinatorial setting, you have discretization artifacts, basically where you have to insert new critical points because you didn't have sufficient grid resolution to represent the flow as it should have been. But as an unbiased arbiter, I'm going to give 2 checks to the topological setting here because we can do simplification and start reasoning about the stability of these things. Okay, so let's look at a simple 2-dimensional example. Here, a bunch of Gaussian blobs, right? We compute the topological dissipation elements. Now we perturb this with 1% of the function value difference at the top right and no perturbation at the bottom left. So you can start seeing that, even with 1%, there's a significant addition of dissipation elements at the top right. The nice thing is if we simplify this, we can get back to the original large-scale function using the topological method. And just to convince you that these two are the actual same function, we have the persistence diagram, so the critical points, the persistent pairs actually match up. Okay, now let's look at that distribution that basically really set the stage for dissipation elements, which was relating the length of a dissipation element to the scalar difference at the extrema. If we take the same approach and simply plot that, the original field, the dissipation elements from the original field are plotted as dots with the Euclidean distance on the x-axis and the scalar difference on the y-axis. If you look at the perturbed field with a tiny bit of noise, you have a completely different looking distribution. And if you simplify it, you recover the original distribution. So this is kind of designed to show that yes, small perturbations can affect your dissipation element statistics. Of course, it's as nasty of an example as you could come up with, though. And similarly, if you look at other kinds of statistics, such as, let's look at the aspect ratio of my average dissipation element, it's going to look a whole lot more like a diamond if we have the original or the simplified versions than if you have the narrow sliver dissipation elements of the perturbed function. Okay, so to be fair, let's look at a 2-dimensional flow rather than an artificial data set. Here again, you sometimes have little strings of critical points in the valleys and along the ridge lines, and we simply apply a 1% persistence filter. That threshold is kind of chosen arbitrarily, but just to show that there is in fact an effect of simplification. So we start out with 562 elements, went down to 190 after 1% simplification. If we look at the cumulative density function of the function value difference, what you see is that the original, that's the red, has a lot more small elements, and it has a correspondingly smaller mean difference in function value than the simplified version. And just to clarify here, this is approximately 25% difference in a core statistic you get by changing your function by 1%. So this may not be the definition of exactly a stable analysis. Same thing happens with the cumulative density function of the Euclidean length between the extrema. You have a lot more short elements in the original versus the simplified. And what's really interesting here, though, is if we look at this distribution of plotting the distance on the x-axis, the scalar difference on the y-axis, and we look at the conditioned mean conditioned on the distance, what actually happens is these two curves pretty much line up, which means this key statistic, which they were basing a lot of their analysis on, doesn't actually seem to change that much whether or not you use the simplified or original dissipation elements. And this is actually very interesting, and maybe we can theorize that, well, it actually happens that all the dissipation elements you created are somehow coherent, that nothing terrible actually happened. So let's look at this in a 3-dimensional case and extend the analysis a bit further. So in 2009, Milano et al. Proposed a technique to identify turbulence zones in flows. So what he has here is, on the top you have oxidizer going one way, on the bottom you have reactant going another way, and we're looking at the mixture fraction field. And somehow in the middle they mix. If you look at the dissipation elements where the minimum is above some threshold and the maximum is below some threshold, those should correspond to the isolated bits of material that have been taken from the top and rotated around, and taken from the bottom and rotated around. So this is a reasonable definition for identifying a turbulence zone. So we take this same analysis and look at one of the data sets from our collaborators, where we have a jet of pure reactant going in and pure oxidizer going opposite direction. So the jet is coming in along a plane. We have a very similar experimental setup, and then we can start asking questions. Well, can we look at how this turbulence zone responds to simplification? So the first thing we do is compute all the critical points that are in the, critical points and dissipation elements in the unsimplified version. This is, here critical points are basically selected based on the mixture fraction of oxidizer and reactant. And then, within a certain threshold, so we don't get any of the minima or maxima either in the pure oxidizer or pure reactant. If we apply just a 1% simplification again, we could obtain a completely different picture. Here, basically, this picture has very few minima inside of this turbulent, what I would think of as the turbulent zone. Instead, it has the maxima, which is basically makes sense. The maxima correspond to pure reactant, and those have been broken up into chunks by the effects of turbulence. Okay, so we extract the dissipation elements from these, and you get on the left from the original, and on the right the 1% simplified. And already now my turbulence zones do not seem to be very stable with respect to simplification. There's very small scale perturbation. And if we just give a cross section of these, they also tell a very different story. Basically, in the original unsimplified version, you could come to the conclusion that the turbulence zone completely separates the top and bottom layers of oxidizer, whereas in the simplified version, you would come up with a completely different story, which is you have isolated patches of this mixing happening. So, what is the correct story? Well, I don't know if there is a correct story. All you can report is the fact that there are these changes. So what we can do is say, okay, we're going to give the number of selected dissipation elements, so the number of dissipation elements inside the turbulence zone, as a function of persistence. So that's this graph. We can also say this is the volume of selected dissipation elements in this range as well, as a function of persistence. So this would indicate that this kind of analysis is not necessarily stable under simplification. Again, we can do the plot of the length versus the function difference versus length, and look at the conditional means. And actually, here's something interesting starts popping out, which is this cluster of lines has lost my mouse. Yeah, this cluster of lines has one particular slope, and after a certain percent persistence simplification, you have another cluster of lines, which may indicate that there are two different modes of how these of the actual underlying physical properties of the thing, depending on what scale you're looking at them. And of course, we would have to do more validation of this and do more experiments to get really statistically significant numbers. But this might, for instance, change the coefficient that Wang and Peters computed initially for the scaling function, the structure scaling function, right? And the cumulative density function and of the function difference in the length also show these similar clustering based on persistence. Okay, so this particular analysis based on the zonal identifying these different zones seems to be unstable. Is there anything we can do with dissipation elements that is still useful? Well, this is a spark-assisted compression ignition simulation where basically you have a spark and there's some background turbulence mixing oxidizer and reactant, and then a flame grows out of it. And here we're going to select all dissipation elements that are involved in the burning process, so their maximum is above 1500 Kelvin. There is something we can do, despite the fact that we still see these kinds of strings of minima in the unsimplified version, and we don't see them in a very slightly simplified version. What we can do is simply say, okay, we're going to report statistics, for a range of perturbation. What we're going to say is, we'll pick our 1% simplification, and this seemed to be what, I won't go into the details of why it's exactly 1%, but what we can do is then go around this and say, okay, if we simplify it more or less, this is how the statistics are affected. And then you can start building stories, say, okay, initially I have a bunch of, these blue lines indicate a bunch of non-burning dissipation elements. The background turbulence causes them to break apart and form new dissipation elements. At some point, ignition takes over, so the proportion of non-burning dissipation elements drops down sharply, whereas the burning ones increase. And then you can come up with some kind of science story that is then, you have confidence that there's an actual physical phenomenon that's going on rather than I have more numerical noise in my data set, and that's what I'm actually doing the analysis on. So of course there are limitations. The technique we're using to do the more small complex computation is inherently slow and serial for now. For example, 12-hour compute time for the spark-assisted compression ignition, and that's only a 560 cube. And of course there's the are we comparing apples and oranges, which is looking at the discrete version versus the numerical version, and it could be that the artifacts you get between the two of them actually make a very big difference, and more investigation needs to be done to determine if this is the case. And another main problem is we can only look at the effect of simplification, not general perturbation. For instance, if we have a flat region with just one minimum on it, or one maximum, then it may be that a very small perturbation of this would create new critical points. And actually this is something where the mandatory critical points could be pretty useful, because if you put a little bound on the top and bottom and then you can start looking at that would be kind of neat. So in conclusion, we reintroduced dissipation elements as the cells of the Morse scale complex. We measured the effect of perturbation on analysis of various statistics on dissipation elements, and showed that some of these are inherently unstable, and also that reporting the instability can still lead you to have a more complete picture of the science use case. So thank you, and questions. And while there are questions, Christoph asked me to show this slide as an advertisement for Top 1 Viz.
You use persistence to simplify.
Yes.
Did you thought about different measures? I mean, in this context, I could imagine that the size of the volume of the dissipation element could also guide simplification, so that you could give maybe more stable, or I don't know, different statistics.
Yes, we thought about it. Oh, the advertisement disappeared. So there was a certain, basically the occurrence of these strings of maxima was very well explained by a small scale perturbation that could be removed by persistence. So it's definitely something that we'd have to investigate more fully, because also the generation of new dissipation elements occurs at a similar scale where high strain starts to break these things into two. And distinguishing between what is actually numerical noise and actually a small scale feature being born is something that needs to be done. One possible way to do it is to actually look at time tracking these things, where if you start time tracking, then you can actually tell when this is actually splitting, because at some point there's going to be a significant difference there.
So what would happen if you use the numerical technique and just go through smoothing and scale space of the data and you get the same changes in the statistics, or is that more robust?
You know, that's a very good question. We didn't do that because for our data sets, the resolution, basically, you're already at the finest, or the grid resolution is, the function already needs the finest resolution of the grid to be well resolved. And what you end up having are these sheets of low value squeezed between sheets of high value. And I would suspect that doing any kind of smoothing would immediately wash out those values. But it's definitely something worth considering.
Just to follow up on that, there are a couple of places where people have looked at Gaussian smoothing, and it doesn't get rid of topological noise terribly well. It flattens bumps, but it takes a lot of smoothing to eliminate them.
I mean, in general, I agree. I mean, I have the same experience, but I was just wondering whether it shows up in statistics.
Yeah, that would be a very interesting question.
So let's start Q&A.